Yeah. Hello. Good morning, everyone. Welcome to the final part of this two-part seminar talks by Associate Professor Ricardo Vinuesa from KTH. Without further ado, I'll hand it over to Ricardo to begin his talk. Thanks.
Okay, thank you very much for the introduction and again for the invitation. It's been a great pleasure being here for this couple of weeks. So today I'm going to be talking about the sensing and control of turbulent flows through deep learning. And this is actually funding. There is this in the middle of the screen on that one. If we can move it maybe from this, yeah, probably that's better. So this is funded by the ERC, the European Research Council, and also the Swedish Research Council. So let's start by introducing a little bit what is the potential. Now the slides don't seem to move. Okay, now it works. So the motivation for this work can be initiated from this slide by Airbus, where we look at the contributions to total drag in a typical airliner. We know that around 50% of the total drag comes from the friction. This is this component over here. You can see the different contributions of different parts of the airplane. The wing is actually around 50% of that friction component. And 40% of the total is associated with the lift-induced drag. And the lift-induced drag has to do with finite wings. When you have this pressure difference, you have wingtip vortices that form from the pressure to the suction side that significantly impact the aerodynamics of the wing. So by looking at turbulent wings which are finite, as I will be showing you in a minute, then we can understand a significant fraction of the total drag in typical airliners. So we use this numerical coordinate 5000. It's based on the spectral element method to produce high fidelity data. Turns out that the spectral element method combines the geometrical flexibility of finite elements with the high order convergence of spectral methods. And this allows us to simulate relatively complex geometries like this one. This is a NACA 4412 wing section. That's a DNS, so you can really see the level of detail that one can obtain. The idea is that if we have good data and good high fidelity data, then we can be in a better position to develop better data-driven and machine learning models. So what we also want to do is go to a bit more extreme flow conditions. What you can see here is a range of Reynolds numbers that we can achieve in our turbulent wings. We go from 100,000 up to a Reynolds number of 1 million. And 1 million is interesting because that's, well, in the range of what can be done in academic wind tunnels. And then the aerodynamics, in this case, start to be similar to those in larger applications. We have a very detailed database in this reference from 2018, where we have statistics, spectra, time series. So if you're interested in the data, we're always happy to share it. But in the meantime, we wanted to go to a little bit more interesting conditions. No, I mean, the turbulent wings that are infinite, these span-wise periodic cases, can give us some information about pressure gradients, turbulence, things like that. But there is one limitation when we come into the meshing. As you can see here, the elements in the far field are very elongated because this is a conformal mesh, and that has quite some limitations in terms of the the pressure iterations, no? that we have to do in order to integrate the governing equations. So what happens is that if we want to go to much higher Reynolds numbers or other more complex geometries, this conformal meshing is actually quite limiting. Still, these cases are quite large, from 2 to 3 billion grid points. So these are reasonably large simulations. But if we want to go to these finite wings that I was talking about before, what we need to do is go into, for example, adaptive meshing. So these capabilities of adaptive mesh refinement in NEC 5000 allow us to automatically refine the mesh in the regions where we need more resolution. So in this white plane over here, you can see how automatically the mesh gets refined close to the wing, it gets coarser in the far field. You can also see that the mesh is non-conformal, which gives us quite some flexibility for the far field simulation. And in these blue planes over here, you can see how we get finer mesh resolutions to track the wingtip vortex evolution. So automatically, the method is able to really track these detailed features that you can have in the flow. This is work, by the way, by Sebas Tosik, who is a senior researcher in my group. You can see in archive some details of these simulations. We conducted a number of cases which are periodic and are finite. And so we have 3 wings that are periodic and 3 wings with a rounded wingtip like this one. And I'll be showing you a visualization so you can get an idea of what the flow looks like. The idea is that for all these cases, we have all the turbulence statistics, again, budgets, spectra, and these are quite large cases. This is, we're talking on the order of 2-3 billion grid points that are resolved with very, very fine resolutions. So if we want to really study a bit of the physics in these cases, you can see, okay, this is playing. You can see the type of flow physics that we are looking at here. So this is a NACA below 12, 5-degree angle of attack. Because you have an angle of attack, you have the pressure difference that creates the wingtip vortex. And this is an almost DNS resolution, effectively DNS, where you can see, well, the prominent effect of the wingtip vortex, which is a very robust feature on the wake, up to many chords downstream of the wing. And you can actually see also the impact of this wingtip vortex on the wake. This lift-induced component that I was mentioning before is strongly associated with the convection of this wingtip vortex downwards on the wake. That really affects the capacity of the wing to extract lift from the aerodynamics. And therefore, that's what adds this extra component of the drag because of the effect of this vortex. So this rotation that you can see here induces a wall-normal velocity on the wake that is negative, a vertical velocity that is negative, which basically changes the locus of the wake, and that's what affects the aerodynamics of the wing. I'm going to zoom in a minute on the wingtip region, so you can actually see what this wingtip vortex looks like and how it affects turbulence. This is just to illustrate the level of detail that we can obtain in our data. I'm showing you, by the way, vertical structures and vortex clusters. So these are very simple lambda-2 visualizations. But what is interesting is that the wingtip vortex produces a quite strong span-wise pressure gradient, which is relaminarizing the flow locally, as you can see now over here. So, and that's expected, no? Because favorable pressure gradients, acceleration of boundary layers leads to, well, possibly relaminarization, which is what we observe here. And this has a quite pronounced effect also in the wake. So the wake really sees how this attenuation of the turbulent fluctuations is affecting its streamwise development. So again, I will not go into too many details of this flow case. This is just to illustrate the type of highly detailed data that we can obtain nowadays, and that this type of data can help us hopefully to inform better machine learning models. Okay, and this was simulated thanks to PRAISE and the ERC, among other funding sources. So essentially, if we try to look at applications of machine learning to fluid mechanics, historically, there have been a number of interesting articles, starting 20 years ago by the work by Milano and Komosakos, where they used neural networks to model the near-world region of a turbulent channel. More recently, there has been quite some work on SES modeling for LES, inflow conditions, boundary conditions, flow control, trans modeling, and also physics-informed neural networks, which I talked about last week, where there is quite some potential as well for experimental and numerical approaches. So there are a number of areas where machine learning helps in the context of fluid mechanics. We actually have a review paper in Nature Computational Science with Steve Branton, where we try to summarize that. And this figure gives an overview of how machine learning can help CFD, computational fluid dynamics. We're actually working on a similar review on experimental fluid dynamics as well. So there is some potential of machine learning on experiments also. But if we focus on the numerics, there is potential to accelerate DNS. There is also possibilities to improve modeling in terms of runs and LES. And there is quite some possibility in the context of reduced order models. And this is something that I will be focusing on in a part of the presentation today. So using machine learning, we can enhance CFD, but in no way replace CFD. We can complement and try to find the areas where machine learning can actually help us to conduct better and more effective simulations. Okay. So this is about kind of like an overview of the context of machine learning for fluid mechanics. Today, I'm going to give 5 examples that we are working on in our group on how we can actually well, use these tools to improve some of the possibilities for sensing and controlling turbulent flows. And I'm going to start with non-intrusive sensing in turbulent channels. By non-intrusive sensing, what I mean is the possibility of using information measured at the wall and then try to use that information to predict what happens above the wall. So that's convenient for flow control, especially if you do closed loop control, because if you know what the flow looks like instantaneously, then you can, well, probably you will be able to control it better, because you know exactly the type of fluctuations that you should be targeting. So we're going to be looking at possibilities of measuring on this blue plane, which is the wall. We're going to consider that we have the wall shear stress components and the wall pressure on that blue plane. And I'm going to predict the velocity fluctuations above the wall. So at different wall normal locations to try to see what the flow looks like instantaneously in those cases. And I'm going to use several computer vision tools, like convolutional neural networks and other tools. This is work carried out mainly by Luca Guastoni, who is a PhD student in my group. You can see all the details in the JFM paper, but I will share the highlights and some of the main ideas of these architectures that we are using here. Okay, so well, the first thing that we did was to conduct DNS of a turbulent open channel. The reason to do an open channel is that the dynamics of the larger scales is slightly simpler in an open channel. If you have a regular channel with two walls, the results are similar. And we consider friction Reynolds numbers of 180 and 550, just to have a bit of a range in Reynolds numbers. And the 550 is already, well, quite turbulent, so it's a quite indicative flow case. And this DNS will be used to establish the mapping between the wall information and the off-wall information. And that's the database that we will use for this. So the type of architecture that you can use, and if you remember the seminar last week, I talked about this type of architecture, this MLP, these fully connected networks. Turns out that, as we know, turbulence has a quite pronounced coherence behavior spatially. There are coherent structures that are highly correlated in space, and therefore there is a lot of spatial information that can be exploited to conduct the predictions. So an MLP, where the information is fed into the input as an array, and you don't really get a good grasp of the spatial distribution of the data, then you will not really be able to exploit those spatial correlations in your predictions. So MLPs are probably not a good choice when you're looking at images, but luckily we have this computer vision field in which we have this type of architecture, which is called a convolution, and this is a convolution operation, in which we can exploit the spatial information in the data to improve our predictions. So this would be my input field, like, well, my image, basically. This little square, this little window is a kernel, which is sweeping through the input image. And this kernel is basically conducting a convolution operation in which each point in the output receives information from 9 points in the input. And we know exactly how the data is organized in space. Therefore, we can exploit those spatial correlations in the data to perform our predictions. So that's why convolutional neural networks are quite convenient when you're working with images and with essentially with data that contains spatial information. So this is one of the architectures that we look at. This is a convolutional neural network with 6 hidden layers. We have 3 inputs, which is the information at the wall, 3 outputs, which are the velocity fluctuations above the wall. These numbers indicate the number of filters that we have in each of the hidden layers. And turns out that even deeper networks are much better for, or actually better for predictions. I will get to that in a second, but even this architecture, it gives us very, very nice results. Turns out that the first layers are identifying simpler features in the data, in the input image, like edges, like regions of recirculation, things that are kind of simple. That's what the first layers are doing. And then the concatenated application of convolutions is helping us to build hierarchically more and more complex features. So towards the end, we are looking at things that are larger and more complicated. So this hierarchical way in which a convolutional neural network learns from images is actually, well, how turbulence behaves to some extent, because turbulence is also hierarchical. So that's why, in principle, it's quite convenient to use this type of architecture for predictions in turbulence. And if we fix the number of parameters and make the network deeper, so we basically reduce the number of filters per layer and we increase the number of hidden layers, we have even better predictions because we can really go at the end to more fine details and that you have in those structures towards really building very complex flow features. So, but even this architecture, which is a bit simpler, performs extremely well for the predictions that I'm going to be talking about today. Okay. So this is what the CNN looks like, and this is the flow setup. So on the left, I have my 3 input fields. On the right, my 3 output fields. We do some padding for periodicity because these fields are periodic, and this is basically the problem setup that we have. Okay. So what I have shown you so far is what we call the FCN method, the fully convolutional network method. Basically, I take a plane at the wall, and I use that plane to predict another plane above. So from image to image directly. But there is an alternative approach, which we call FCN POD, that relies on POD, on proper orthogonal decomposition, in which we tessellate our domain into these smaller subdomains. For each of these subdomains, any scale larger than the size of the domain will be lumped into the first POD mode, which means that computationally, by choosing correctly the size of these subdomains, we can make the problem more computationally tractable. We don't need to predict so many temporal coefficients. And well, essentially what we do is that we decompose the spatio-temporal problem into spatial modes, and we'll need to predict the temporal coefficients. That's what we do with this POD-based approach. And we're going to compare the performance of the FCN and the FCN POD in different regions of the flow. So we're going to see how things actually work in different places. So what I'm showing you in this slide is the stringwise velocity fluctuations, instantaneous. The first column is y plus 15, so in the near world region. Second column, y plus 100, that's in the outer region at eta of 50. The third row is the DNS, so this is the reference, and this is what I'm trying to predict. And the first row is a prediction based on extended POD. Extended POD is a linear method, formally equivalent to linear stochastic estimation. So as we know, turbulence is inherently nonlinear. There is one linear component, which is the superposition, and the linear superposition on the large scales on the wall. That's linear, and that can be reproduced by the extended POD. But the nonlinear modulation, that cannot be reproduced by a linear method. So all the details of modulation of scales that happen in turbulence, well, that in principle cannot be predicted by this. No? And that's basically what we see. The fluctuations compared with the third row, they are attenuated. And we are missing details, particularly in the nonlinear variation of those streaks. No, we're really missing that modulation aspect that is more nonlinear and more complex to predict. That's why we believe that the convolutional neural networks are going to predict better than the linear method. And if we look at the fourth row, that's the FCM. That's where we use the whole plane to predict another plane. We see that the agreement at y plus 15, so these two panels, is actually really good. So the instantaneous prediction is excellent. I'm going to show you in a minute the statistical results, but instantaneously the flow looks really good. And the FCM POD, the one based on the POD approach, that performs better far away from the wall. So basically, these two panels is what I'm comparing now. So it turns out that close to the wall, doing POD is not really worth it because you're just better predicting the whole field directly. But farther away from the wall, since the flow is dominated by fewer, very large scale streaks over there, those can be modeled more effectively with POD. And then it's more effective to just predict the temporal dynamics of those POD modes that encapsulate quite well the large scale dynamics in that region. So close to the wall, the FCM works better. Far away from the wall, then you want to combine it with POD, basically. So this was the instantaneous performance. If we look at the statistics, I'm showing you the stringwise, wall normal, and spanwise velocity fluctuations. The black line is the reference from the DNS. The square is the FCN. The dots, the blue dots, are the FCM POD, and the squares are the extended POD. That's the linear method. And what we can see is that the linear method underperforms. The predictions are worse than the other neural network-based approaches. Close to the wall, the near wall peak with FCM method, we basically nail it. We get less than 1% error. And farther away from the wall, the FCM POD starts to get better. And so then the error of the FCM POD is around 26%, which is still quite reasonable. Keeping in mind that with the farther away that you have the input and the output, the more challenging the prediction, because the data is less correlated. Right? So predicting the outer region is not so easy, but the predictions that we get are quite okay with the FCM POD. Okay, so this is about the potential to predict the flow from the wall to above the wall. And that's basically the idea. There is one approach which I believe is very interesting, and it's what we call transfer learning. So in transfer learning, you can take whatever you learn in one case and try to extend it to another case, which is not too similar, but not too different from the original. So you can retrain a network by exploiting information that you already know from another case. So what we show two cases of transfer learning. In the first one, we are showing you at one particular Reynolds number, we take one network trained to predict at y plus 15, and we're going to see what we can reuse for y plus 50, so farther away from the wall. And if you remember from before, the first layers are looking at simpler features and smaller features, which in principle are more similar close to the wall and farther away from the wall. And the larger scales that are going to be predicted by the last layers, those ones will change close to the wall and farther away from the wall. So what I do is that I am fixing the first three layers, and I'm retraining the three last layers to really see if we can improve the performance of our network. And it turns out that, yes, we can get, well, in terms of accuracy, we get the same errors, the same accuracy as with the original network, but we reduce the training time to 23% of the original. So by reducing the information that we knew close to the wall, we can actually save significantly in terms of training time, which is in principle good. Perhaps even more interesting is transfer learning from low to high Reynolds numbers. So we basically take a network that was trained to make predictions at Arita 180. We take the weights of that network and we put them in the network at 550, and we keep training after transferring the weights from low Reynolds number. And we compare the performance of the network with the transfer weights with the performance of a network where the initialization was random. And it turns out that the loss function, the predictions are equally good, but I can reduce the amount of training data again by a factor of 4. So once again, I can significantly increase the efficiency of my training by doing transfer learning. And in this case, it's actually quite interesting because the 180 case, we can run it in a laptop, right? And the 550 case is significantly more expensive. Now you need a bigger machine. So if I can do most of my training in a case that is so cheap that I can run on my laptop and I can minimize the need of quite expensive data, then I'm doing something good with the design of my network and with the capabilities of training my architecture. So transfer learning, I believe, has a lot of potential in fluid mechanics and to try to go to progressively more complicated applications. Okay. So far, I've shown you the first example where I'm predicting information above the wall from information at the wall, but I'm using DNS data, right? So I'm assuming that I have DNS resolution at the wall. In reality, that's not going to be the case. In reality, if I put this in an experiment, the resolution at the wall is going to be much coarser. So what we do is that we use another architecture to first downsample the information at the wall. So with coarse information at the wall, I want to see what type of predictions I can actually get. And in this case, I'm going to use an architecture called GAN. This is a neural network that contains two parts. These are generative adversarial networks. The first part of this architecture is called the generator. The generator is producing high resolution images from low resolution ones based on a reference data set. So I'm reproducing the statistical distributions of this data set. And the second part of the architecture is the discriminator, which has the job of assessing whether a particular image is real or if it was produced by the generator. And of course, these two parts of the same network, they have antagonic roles. So we can train them together using game theory in such a way that we end up with a generator that is really good at producing high resolution data that looks very realistic. That's a little bit the idea. So our architecture will have two parts. In a first step, we're going to take low resolution data at the wall and produce high resolution data at the wall. Having this information, we will then predict the flow above the wall with the high resolution information from the wall. And to give you an idea of the performance of this type of architecture, I'm showing you at the bottom the instantaneous string-wise wall shear stress. This is the DNS, so that's the reference. In the first row, I'm downsampling, so I'm reducing the resolution of that field by a factor of 4, 8, and 16 squared. So I'm really making it coarser and coarser. Turns out that this field over here, almost by accident, but the resolution that you have in this field is basically the resolution that you would have if you have an array of microphones or an array of pressure sensors. So more or less, this is what you could get in an experimental setup. And then on the second row, I'm showing you the predictions of the wall shear stress that we want to compare with this panel over here. Now, keep in mind, this one that you can see, you are losing completely the coherence in the data, no? Because it's point measurements where you don't really reproduce the structures, you're really reconstructing a lot. But it turns out that the predictions are always quite realistic. In fact, in this case, the agreement is pretty good. As I go towards higher and higher downsampling, the fluctuations are attenuated. But the interesting thing is that I can reproduce the streaks. I mean, the streaks are where they need to be. They're as long as they need to be, and the spacing is correct. So if I want to control streaks, even from quite coarse measurements, I can get reasonably good predictions of those streaks. And this is work together with Carlos III University. This is published in Physics of Fluids. So again, all the details are there, so you can check them out. If I want to predict above the wall, then we can look at the performance at different wall normal locations. This is Y plus 15, 30, 50, and 100. The first row is the DNS. And as I go down, I'm increasing the downsampling. So I'm trying to predict farther away from the wall and using progressively coarser data. And this is, by the way, the string-wise velocity fluctuations. Clearly, the easiest prediction to make is this one, right? These two panels, because the data is close to the input and the downsampling is quite low. And you can see that the prediction is still really good. As we saw before, the Y plus 15 data is very well predicted, even with a small downsampling. The most challenging prediction is this one over here, the bottom right panel, which we want to compare with the top right panel. So these two over here. And of course, that's more challenging because the input is very coarse and the data is very far away. But still, what you can see is that we can extract the location of the large-scale streaks. So I can actually find them. Of course, with quite some limitations, we're losing a lot of the details, but we are able, if we want to do large-scale control, we can still identify those features there. So in principle, there is quite some potential also from this GANs architecture if we want to predict the flow and try to devise possible flow control strategies in the near wall and also in the outer region. Okay, so this was about sensing the flow from quite coarse inputs. Now I'm going to show you one example of the opposite application. So instead of predicting from the wall above the wall, I'm going to use information from the outer region to predict what happens closer to the wall. And of course, one motivation for this is in wall models. We're not going to develop a wall model. This is just kind of like a prediction exercise. This is work in archive, and you can see the details there. We're working on a paper on it also, so that should be available soon. And the idea, this is actually something that follows a little bit what Mizuno and Jimenez did 9 years ago. So what they did was that they took a channel at Tau 1000, and then they look at the overlap layer. And of course, there you have cell similarity of the scales. So they took the plane at y over h 0.2, rescale it with a difference in y, and put it as a boundary condition at y over h 0.1. Okay, and that's well, a bit an assumption on the possibility to rescale that plane. What we want to do here is if we can predict the plane close to the wall, again within the overlap layer, based on the input plane above the wall. So my input is at y plus 100. My output is going to be at y plus 50. So that's my boundary plane that I would use. This is the DNS. And the prediction is shown in the third row. The first column is U, second one V, third one W. These are instantaneous velocity fluctuations. And I'm comparing the third row with the second one. And you can see that the U component is in pretty good agreement instantaneously. So actually, I can get quite good results. V and W are okay, but they exhibit more deviation. And here I want to highlight that predicting from far away from the wall to predict closer to the wall, that's much more challenging than what we were doing before, for two reasons. The first one is that we're missing the small scale information. I mean, when you use the wall information to predict above, the small scale information is there. Here we don't have it because we're using large scales as my input. And the second problem, or the second challenge, is that when you have a very large scale, the receptive field is quite small compared with the input information of that structure that we're having. So one needs to really rework a little bit how you're doing the pooling to be able to fully exploit the input data with the receptive field that we're using. But even with these challenges and these limitations, the spectra is not so bad. This is the power spectral density at wavelength 50. The shaded contours is the reference, and the orange lines are the prediction. So of course, we are missing the part of the small scales, that's expected. But actually the larger scales over here, they're quite okay. And then V and W exhibit a bit of deviation in the spectrum. That's where one can try to get some improvement. In any case, the U prime is predicted with 19% error, which is quite good in principle. Some possibilities to improve these predictions could be to use a GANs architecture. This was, by the way, a convolutional neural network. With a GANs, we could aim at reconstructing some of that small scale information that is missing, and to play a little bit with max pooling and renormalization of the data to be able to extract the input information more effectively. So those could be possible improvements. And by the way, here we're not claiming that we are developing a wall model, and this is just a prediction exercise to do a wall model that works a posteriori. That's another story. But as well, basically as an assessment of what can be done, is an interesting possible exercise there. Okay. Now, I promised you at the beginning to talk about reduced order models, and here I believe there is quite some potential as well of neural networks. So of course we all know POD and how POD can, well, from a linear point of view, produce an optimal reconstruction, an optimal reduced order model of the data. That optimality is very interesting from the linear point of view. And the other interesting property of POD is that by construction, it gives us orthogonal modes, which means that they're going to be very interpretable, not from a physical point of view. The only problem of this of POD in principle is that when you apply to turbulent flows, where you have nonlinearities and a very broad range of scales, you need many modes to be able to reconstruct significant fractions of the energy. In this sense, autoencoders, which I'm going to be discussing in this part of the presentation, they are neural networks which allow us to exploit nonlinearities that are also designed to compress data. So if we can combine the nonlinearities with the optimality and orthogonality, then we would get a quite interesting approach for turbulence. And that's what we did in this work, publishing expert systems with applications. The data and the codes are available to share also. And this, if you want to collaborate on this, I'm happy to discuss more and share more. And I will start by explaining the type of data that we will be using. This is, again, DNS-like resolution of a simplified urban environment. So I have two obstacles. I have many databases where I separate the distance between the obstacles, and I have arrays of cities, but this is just the simplest flow case. There's a couple of papers where we document the database, and you can see the level of detail that we obtain in terms of the vertical structures. So this is a very well-resolved flow case. We have over 1,000 instantaneous fields, and we're going to consider a horizontal plane at half the height of the obstacles. So that horizontal plane will be basically the reference data that we're going to consider. The reason why I choose this flow case is because, I mean, on the one hand, it's, well, you have, wakes, shear layer separation. So POD should not be too bad because you have quite pronounced features. But at the same time, you have turbulence and quite some nonlinearity, which means that POD will not be perfect. You will need quite some POD modes. In fact, you need on the order of 400 or 500 POD modes in this case to reconstruct a good fraction of the energy. Of course, in an internal flow, it would be even worse. And we're going to see if we can do better with these autoencoders that I'm presenting today. So an autoencoder looks like this. In fact, we're going to use a convolutional autoencoder because, as we saw before, turbulence has quite pronounced spatial information that we want to exploit with our network. So using a CNN in this autoencoder architecture will be beneficial. And an autoencoder is, in a way, a bit of a boring network because your output is supposed to be the same as the input. You're trying to reconstruct the same signal that you have. The key here is that in a first part, which is called the encoder, you're trying to reduce the dimension of your data so that in this so-called latent space, you can obtain a very compressed representation of the original data. And in the second part, you are increasing the dimension of your data again. That's the decoder. Right? So the loss function of this architecture is the difference between the output and the input field. And that's the loss function. And what you're hoping is that in this bottleneck, in this latent space, you can really compress the data quite significantly, exploiting the nonlinearities that you're having through the successive application of these filters that we're having here, these convolutional filters. So, of course, the autoencoders are very good at compressing data, but they don't give you modes that are orthogonal, and they don't tell you anything about ranking those modes in terms of their reconstruction contribution, right? So the physical interest is a bit limited, I would say. The possibility of ranking the modes in terms of the reconstruction, this is something that Fukani and others address. This is Koji Fukahata's group, by using the framework of hierarchical autoencoders. So in the hierarchical autoencoders, what you do is that you start with one autoencoder and the latent space is fixed to a dimension of 1. So you will only get one latent vector. This is R1. So this is my first autoencoder. Then you go and create another autoencoder with a dimension of 2 in the latent space. And you fix the first vector that you obtained before. So R1 is fixed. Now you only obtain a new vector, R2. And you do that recursively in a way that each new latent vector that you're adding is having less and less contribution to the reconstruction. So in that hierarchical framework, you're finding a way to rank your modes in terms of their contribution. So that's in principle interesting, but this will not give you orthogonal modes. And you can look at that sort of optimality if you wish. That's defined quite differently because this is all nonlinear, but some sort of optimality, some sort of ranking of the modes, but these are not orthogonal, which is also what we want. In order to see if we can obtain orthogonal modes, we go into the framework of the beta variational autoencoders. So in these variational autoencoder approaches, we can introduce stochasticity in the latent space. So we can actually sample from it. If you look at some definitions, P of X here will be the distribution of the original data. P of R will be the distribution of the data in the latent space. And the goal is to maximize this function, which is the marginal likelihood. That's the approximation of P of X given the parameters theta of the network. Okay. And in this framework, we have two conditional probabilities. This first conditional probability takes me from the latent to the original space, which means that this is a decoder. And because we're perturbing the latent space, this is a generative model. So we are having a generative model here. The second conditional probability takes me from the original to the latent space, and that's the encoder, which is a recognition model. So these two are distributions of data, which in the framework of the beta variational autoencoders are assumed to be Gaussian. So the encoder distribution is assumed to be Gaussian. That means that the latent variables are going to be defined by a mean and a standard deviation. And I can perturb this latent space with a Gaussian noise. So actually, I can define these latent vectors like this, and I can sample from those latent vectors. I can get the sampling from those. The loss function of these beta variational autoencoders looks like this. So this loss function has a first term, which is the reconstruction. I want to be able to reconstruct the original signal through my bottleneck. And the second term, which is regulated by this hyperparameter beta. And that's why that gives the name to the method, not so original maybe. And this term, what it's doing is promoting learning statistically independent variables in the latent space. So in a way, what you're aiming at is having a latent space that is made up of statistically independent variables, and that is quite parsimonious, that many of those variables are actually 0. So we can have a disentangled and parsimonious latent space, and that's a bit the goal. And if beta is 0, then I'm converging to the normal autoencoder. If beta gets higher, then the modes will be more orthogonal but my reconstruction will get worse, no? Because at the end, you cannot have it all. So you need to regulate your loss function and regularize it in a way that you can promote whatever you want in terms of the parameter beta. Okay. So this is what my architecture looks like, my decoder, my encoder, and this is what the latent variables in the latent space look like with the mean, standard deviation, and the noise. So let's look at the stringwise velocity fluctuations. This is an instantaneous flow field. I'm showing you reconstructions of the data with 5 modes. The POD gives you around 30% of reconstruction, and you can see that the flow is really filtered compared with the original data. You're missing most of the details. The 3 autoencoder-based approaches reconstruct around 90% of the energy. So with 5 modes, you can get a pretty good reconstruction. Remember that POD would need on the order of several hundreds of modes. With 5 autoencoder modes, I'm doing pretty much fine. And if we zoom in the region between the 2 obstacles, we can see this, these pronounced features of high and low speed, which the POD misses. The POD doesn't identify those features, but the 3 autoencoder approaches are able to identify. So in principle, the nonlinearities that we are leveraging with the autoencoders are allowing me to get a quite compact reduced order model, which identifies relevant features in the data. Now the point is, okay, in terms of compressing, these autoencoders are good. That's what they are designed for. But what about the physical interpretation of those modes? That's where the orthogonality comes in. And if we look at the orthogonality, this is the determinant of the cross-correlation matrix in latent space, but in physical space, it looks the same. The POD is, of course, having 100% orthogonality by construction, and the beta variation autoencoder gets over 99% orthogonality. So the off-diagonal terms are almost 0 in all the cases. However, the 2 other autoencoders, the convolutional and the hierarchical, are only having around 87% orthogonality, which means that they're really not orthogonal modes. And that's a problem if I want to be able to have some interpretability, because that means that a particular physical mechanism is going to be mapped into a variety of modes. So I cannot really decouple the phenomena that I have in my flow, in my data. That's why the beta variational will be more interpretable. This is the effect of the hyperparameter beta. So of course, if I make beta larger, my red line, which is the orthogonality, that gets higher. I'm promoting learning more orthogonal modes. But at the same time, when I make beta higher, the blue line, which is the percentage of reconstructed turbulent kinetic energy, that gets smaller, because the reconstruction loss gets less weight, and the model is trying to learn modes that are more orthogonal. So of course, you want to find a sweet spot in this figure. And as you can see here, these are the latent variables. When I am making or I'm promoting higher beta values, then there are few non-zero variables in the latent space. And so that's a little bit what the topology of the latent space looks like when I'm trying to change these hyperparameters. Okay. And this is a little bit of an interpretation of these reduced order models that I'm building. I'm showing you the first 5 modes. And the second column gives me the POD. So this is basically the standard POD. We can identify in the first mode quite easily the shear layers, large scale separation, vortex shedding, and then the additional modes contribute to higher frequencies into this phenomena. That's what we expect. What is interesting is the third and fourth columns, which are giving me the autoencoder and the hierarchical autoencoder approaches when the modes are not orthogonal. And what I get is basically noise, high and low frequency noise, but nothing really physical comes in those modes. It's very good at compressing. I can compress the data very effectively, but I can't really interpret any physics from this. In the first column, I'm showing you the beta variation autoencoder, which is giving me orthogonal modes. And what is interesting is that the first autoencoder mode looks a lot like the POD mode, and you have the same features, the same large scale separation, you have the shedding in the wake. Of course, the higher order modes are giving me additional details of the wake, because with POD you need many more modes to look at the same stuff here. But essentially, what we see is that with the autoencoder approach, we have modes that look a bit like the POD with higher frequency components, with with the turbulent fluctuations superimposed on those features. And that's interesting because that's basically allowing me to combine many of those POD modes into only one, and well, get similar features, but where I need to use this for predictive temporal predictions as a reduced order model, then I only need to worry about 5 modes rather than 500. So in principle, I believe that autoencoders, in particular these beta variation autoencoders, are really giving me a lot of potential to build reduced order models in turbulence, no? When we really have this very broad range of scales, and then POD doesn't really help so much. And by the way, this algorithm over here allows us to recursively sort the modes and establish the ranking. So with the beta variation, I get modes that are orthogonal, and they're also ranked in terms of their contribution to the reconstruction. Okay. And okay, so the last application of today, because in the title I mentioned flow control, so we also look at flow control with deep reinforcement learning. Okay. So a very short introduction of what reinforcement learning looks like. This is work also by Luca Guastoni, who presented it in the APS. We're working on a paper to release quite soon all the codes and all the data. The idea is the following. In the reinforcement learning framework, you have an agent, which in this case would be the neural network, which is interacting with the environment, and the environment would be the CFD solver that contains the flow that we're looking at. And we want to do flow control. So we're going to do, well, we're going to perform actions on that environment, and the environment is going to react in 2 ways. It's going to change its state, and it's going to change, it's going to provide a reward. The reward is set by us, basically. The reward is a measure of the quality of those actions under a certain norm, whatever that means. If we want to define drag reduction, if we want to define enhanced mixing, and the agent will find its way to maximize the reward. In fact, the goal of reinforcement learning is to develop a policy pi, which, given the state of the system, chooses the right actions to maximize the expectation of the reward in the long term. And that's a little bit what we want to do with reinforcement learning. Now, if you do this for flow control, you have the potential of maybe discovering novel control approaches, because you're not telling the controller what it needs to do. It's just trying by itself possibilities until, you know, it kind of reaches something that could be more optimal than traditional methods. And the first case that we look, that we analyze is quite simple. It's a 2D channel where we induce a separation bubble through suction and blowing at the wall, at the upper wall. So we have this recirculation length, and through control upstream of that bubble, we want to minimize the length of the separation region. So we will compare periodic forcing at a particular frequency, which is the classical solution for this, with the possibilities of doing deep reinforcement learning. And to do that, this is what the setup looks like. So the color region is the negative velocities that you can see here, the separation bubble. The squares are probes where I'm measuring the flow, basically. Sorry, those points over there. This square over here is the place where I set up the actuation. And the actuation is modeled as a body force to mimic blowing and suction. You can really do blowing and suction. I'm learning the amplitude of this forcing to set up the actuation. And my goal is to minimize this arrow over here. Now I want to make the bubble as short as possible. So what is interesting, if we look at the results of this approach, here on the left, I'm showing you a little video of what the reinforcement learning is doing. And of course, periodic forcing will be basically a sinusoidal at a particular frequency. With reinforcement learning, you have one frequency associated to the spacing of these wave packets that I'm sending, and then another time scale, which is connected with the length of the bubble. So you have at least 2 frequencies. So the DRL is finding a more nuanced control that can, well, try to get something that is a bit more advanced than periodic forcing. And if you compare the performance, DRL achieves 30% reduction of the bubble approximately, and the periodic forcing only 20%. So in principle, comparing with a classical solution, the reinforcement learning gives me better performance in this simple flow case. And the last example of today is application to a turbulent channel. So these are very recent results. What we did was we took a turbulent channel at Arita 180, and we compare with opposition control. So opposition control, which is schematically shown here, is a flow control strategy in which you sense the fluctuations in the near wall region, you sense the vertical component, the wall normal component, and at the wall, you impose a wall normal velocity that opposes those fluctuations. So if you have a negative velocity in the near wall, you impose a positive velocity at the wall. And if you have a wall normal velocity that is positive, then you want to suck down, right? You need to really try to oppose those fluctuations. The idea is good because you want to attenuate the turbulent fluctuations, but this model is a bit crude, no? It's a little bit too simple. So what we did was to set up a channel where each grid point had its own possibility to set up its own control, and that was optimized by reinforcement learning. We did it first in a minimal channel at Arita 180, and we obtained with opposition control 23% drag reduction, with reinforcement learning 34%. So we actually outperform the possibility of drag reduction from the classical solution, the opposition control. This difference is also present when we apply the same policy in a full channel at Arita 180. So when you have more complex dynamics, this is still true. I really believe that reinforcement learning has the potential to give us more nuanced and more sophisticated control strategies. It's really able to discover something that is a bit more complex than the classical solution that we are, well, maybe biased to impose in the flow. In fact, it is also able to find different strategies at different Reynolds numbers. This is something that we published last year in actuators. You can see the paper and all the data here. This is a 2D cylinder over a range of Reynolds numbers. And at low Reynolds numbers, the DRL is what it's doing is actually trying to attach the boundary layers into the cylinder to minimize the wake. But then when the Reynolds number increases, it's actually energizing certain structures to try to go to the drag crisis regime that achieves better drag reduction than just trying to attach the boundary layers. So it's actually able to find the different physics that are present in different regimes and exploit those to get good drag reduction performance. And of course, this is only the beginning. There's much more stuff to be done and to improve, but I believe that there's quite some potential also in the context of flow control with this. And this is a summary of my presentation. I showed you about sensing possibilities with computer vision, nonlinear model decomposition with autoencoders, and the capabilities of reinforcement learning for flow control. Again, as last week, this is my contact information, so feel free to reach out if you have any question, if you want to discuss or you want to collaborate on something. And for now, I want to thank you again for your attention, and I will take your questions. Thank you very much.
Thanks, Ricardo. An excellent presentation again, and
thank you so
very
much.
Interesting applications. I'll open it up for questions now, but as before, anyone on the audience can go ahead first. If you have any questions, please feel free to unmute and ask, or type it in the chat and read it off. Thanks. Just a second.
Hello.
Yeah, Lorenzo, go ahead.
Yeah, thank you. So I have fundamentally two questions. The first is related to the CNN, and specifically, I would like to ask which type of preprocessing of the images, how do you prepare your images, which field you would use, you select, and if there are some fields which are better than others, it's beneficial to use maybe different fields, or so all this stuff and related to the preprocessing.
Yeah, I mean, the volume was a bit low, maybe if we can, but I think I understood the question. So you're talking about which of the, we have three fields at the wall as an input, the wall shear stress components and the wall pressure, and all the results that I showed today are based on the three fields. But we played a little bit removing certain fields. We use some explainability of deep learning as well. And we also consider in an experiment, the easiest thing to measure is the pressure. So using only the pressure field, the results are worse, obviously, but of the same order of magnitude. So it doesn't change very, very much. If you want to predict very well the U prime, then the streamwise wall shear stress is the best variable. It's most highly correlated. But if you want to predict everything, the pressure is still, just using the pressure is still quite good.
Thanks. Second question is practice the same, but just apply to the gun. So do the guns.
Lorenzo, can you just speak up a little bit?
Oh, yes, yes. So the second question is the same, but related to the GAN. So do they have some additional requirements as the input, or in principle you could use the same picture from the CNN applied to the GAN?
You can use the same features. In fact, if you use full resolution fields without any downsampling, the GANs performs better than the CNN. The GANs is a more advanced model, it's more complicated, it's also harder to train because it has more parameters, but it performs better, and whatever applies to the CNN essentially applies also to the GANs.
All right. Last question is related to autoencoders. And I would like to ask, have you tried to use a simple autoencoder? So you lose the spatial correlation, and if yes, how do they perform instead of using images, just raw data, tabular data? Is it meaningful, possible, reasonable to do?
So what type of data? I mean, we use images because we have flow fields that we want to, compress. So when you're talking about simpler data, what are you talking about?
Just tables of data, numbers, not images.
Yes, yeah, I mean, for that, you can use fully connected autoencoder, for example, or even a fully connected autoencoder with temporal information if you want to get something from the temporal dynamics. And that works very well in general. I mean, we haven't applied it because we were more interested in looking at the flow fields and compressing the flow fields. But in the literature of machine learning for time series prediction and model reduction, that works well. Yeah. In fact, if you think only of temporal predictions, they're pretty good also for reconstructing sequences in time with quite, a lot of compression and quite good reconstruction. So in principle, it should work pretty well, yeah, at least based on the literature.
Thank you.
Okay, thank you for the questions.
Thanks, Lorenzo.
So with DRL, have you done any comparisons with a classic adjoint solver to see any comparisons?
To optimize the control, we haven't done that. I mean, that's very costly, and especially when you go into turbulence, probably it's not going to be super feasible. Yeah, but it's certainly another possibility and another possible comparison. Yeah. Our approach was to compare with the classical opposition control, which was the
Thanks for really impressive body of work. Unfortunately, I missed your talk last week, so this may have already been addressed, but
thank you.
Is there any ability to sort of hybridize these different architectures? Can you put a physics-informed neural network in a GAN? Is that none of it's straightforward, but is that a relatively straightforward thing where you can leverage the strengths of them both? Or is there something that precludes that kind of mixing of the strengths of the different architectures?
So when you're thinking of a physics-informed, I mean, there's two things. Physics-informed neural networks, in the sense of what I presented last week, is basically solving the governing equation using the machinery of the neural network. But if you're thinking, so that's basically one way to do it. And one can do it with fully connected networks. You can have CNNs and things like that to try to improve the performance, but that's kind of like one route. If you're thinking of, let's say, physics in restraining or imposing physics, which is maybe what you're thinking about, right? That's another thing, which is, I think it's very important to do it. And for example, you can impose, incompressibility, like you can, but it's a combination of imposing things in your architecture, but also imposing things with your data. I mean, if you have the free velocity components, you can, do the vorticity wall normal formulation and impose the incompressibility, let's say, implicitly through the data that you're using. And now you know that your data is incompressible, and you can, from those two variables, recover the other three. That would be one way of imposing, let's say, implicitly through the data, physical constraints. To do it more explicitly in the architecture, I mean, of course, it can be done, and people are doing it. Also with the autoencoder, trying to impose in the latent space some physical constraints. It's something that is an active area of research. So it's, let's say, not super straightforward, I would say, but I believe it's one of the ways to go. To as much as you know about a particular problem, you should put it in the model that you're using. Yeah, absolutely.
Thank you once again.
Thank you for the great presentation. So
you.
I actually have two questions. One is about the autoencoders. So with the POD formulation, we have a clear kind of separation of scales, right?
Yeah.
So large scales kind of are responsible for the, well, coherent structures and the sustaining process. And the smaller scales should be related to dissipation, for example, which leads to stabilization of these scalarity models and everything. So do you have the same kind of physical interpretation using autoencoders? Because you do have both large scales and small scales in a single mode, right?
Yeah, no, here you don't separate into large and small scales. I mean, let's say that the strength of the autoencoder is that you're compressing the data into modes that incorporate that, that range of scales into one particular coherent thing. If you want to do the analysis of separating scales, well, that's not something that you can do. That's not the right tool to do that, basically. You would have to use POD or something else. If you want to look at temporal scales, you can look at DMD. But here, the convenience is more from the computational point of view, because if you want to make, advance this in time, and you can do that in the latent space, then you only need to advance 5 modes, basically. That's the idea.
Yeah, which does make sense, because if you don't include like the smaller scales, then your model will probably blow up, right? So
yeah,
it's really nice. And the second question was about the what's the name of it? The prediction problem, right?
The what?
The prediction problem.
The prediction,
from
yeah.
the wall
Yeah.
to large scales and vice versa, right?
Yeah.
So have you considered using a resolvent-based estimation for this case also?
So that's a good question. I mean, first of all, we did some time ago with the people at ITA with transfer functions, spectral transfer functions, and there, if you have a linear transfer function, you get something similar to extended POD. If you add nonlinear terms, you get better, and then you converge eventually to a CNN or something like that. Resolvent, I know there's quite some nice work by Aaron Tone and company, and they have done it first statistically, so just getting the profiles. But now, I mean, recently I was talking to them, and they're looking at these things also in time. So kind of like unsteady predictions in time. And I mean, they're getting very promising results as well. So I think that's one of the things that could be quite nice to make such a comparison, back-to-back comparison, and see the computational performance and also the reconstruction performance. Yeah.
Yeah, I was wondering if you could like associate both actually, because you do need information about the forcing or the non-linearity of the system to make good predictions in the end, right? Can't really use the white noise assumption for everything. So maybe this could be an approach, like use this kind of machine learning alternatives to predict this component, and then.
Yeah, they can complement the methods. Yeah, I mean, I think so. Even combining linear and nonlinear methods, like you use a linear method to predict the superposition, and then you use the neural network only for the modulation part. That's another possibility. But I really think there's a lot of potential with the resolvent, and that one can investigate a bit more how to combine methods, basically. Yeah.
Thank you.
Thank you for the questions.
Thank you for the great talk.
Thank you.
Just a quick question on the urban bit.
Yeah.
How good was the model in predicting the behavior between the two buildings, between the two, like in this particular spot? Are we able, for example, to use this learning in order to understand, for example, things like the courtyard effect and stuff with less computation time, and like with this size of building, what enhances the courtyard effect, what reduces stagnation, things like that? Are we able to answer things like?
So that's a very good question. I mean, for one particular configuration, you can see, I mean, the level of detail that we get is quite high with this reduced order model. And of course, this is done for a 2D plane. So extending this to 3D would be more computationally demanding, but it's feasible. I mean, I think it's pretty much doable. And this is for one particular configuration. So for that particular configuration, what you get is a reduced order model that reproduces that pretty well. It's actually really good. Now, the next question is how to generalize this, right? So how can I use a model that is trained on this configuration, and then it can generalize to a case with larger separation between the obstacles and things like that. And that's not so straightforward, but we're looking into that, into possibilities to do that. So I believe that variational autoencoders are also able, within the latent space, to learn how the flow depends on geometrical parameters on the data, basically. So that's actually one of the things, and some preliminary tests are quite promising, that you can, let's say you have 3 separations and you train the same model on those 3, and then you want to generate data for another separation that was not in the training data set, and the results are pretty encouraging. So it seems that it is possible to go in that direction. So basically, you train a variational autoencoder such that in the latent space, you can learn dependencies on geometrical parameters of the data.
Now, another follow-up on this,
Yeah.
from the question that was asked previously by Dan. If we used a very coarse CFD model in order to create some sort of a new boundary that we kind of know about from the CFD,
Okay.
does that help us to understand this area a little bit more faster than actually simulating the entire thing using a fine mesh model?
So you're saying that you want to create a boundary condition from a coarse simulation, and using that you run the finer simulation?
Kind of. So try to predict using the simulation another point in time than the other two fixed boundaries that we already know about.
Yeah.
Predict one using CFD, and then use that in order to kind of interrelate and generate.
Yeah, I mean, I guess, yeah, I think what you're suggesting is to go into a multi-fidelity framework where you have data of different fidelities somehow, and then you can, and essentially make a parameter space where some of the points are with higher fidelity, some of the points are with lower fidelity, and you can get, and there are nice statistical frameworks to do that. So yeah, the multi-fidelity framework is looking at that type of thing, how you can combine different fidelities. And of course, reduced order modeling is one part of that, where you can get, I mean, the thing is when this autoencoder model is trained, evaluating that is very fast. You don't need to run that. You can integrate that in time super easily, right? It's very cheap. And of course, you retain, because with POD, you would only retain few of the large scales, but with this, you can really retain a lot of the details. So I think that in these multi-fidelity frameworks, this sort of stuff with autoencoders can actually become an integral part of those methods. Yeah.
Thanks so much.
Yeah. Thank you for the questions.
Yeah, thanks once again. Great presentation.
Thank you.
Seen some very impressive results in there.
Thank you.
What I'd like to know is how you think these will apply to their actual intended target. For example, we're learning flow control. How would that perform in an actual flow control situation? And for example, you're predicting towards the wall in CFD. How would that perform as a wall model, do you think?
Yeah, no, so that's a good question. I mean, the idea of this is to go into an experimental implementation. I mean, to do the sensing experimentally. That's why we looked at this, this downsampling, because we want to use these methods in an experimental data set, and also to implement the flow control and the DRL in an experimental data set. No, that's kind of like the final goal. Here, there's a couple of things. I mean, first of all, we use DNS data to train our models because you have all the details, of the flow, and the network can probably exploit the information quite effectively there. In the simulation, you would not have access to all the data when you do the experiment. But of course, you need to, in your training data, be able to reproduce the experimental errors, let's say, or the experimental lack of resolution. And that does not only mean to reduce the resolution, but to take into account the filtering effect of the sensor, uncertainty in the probe position, noise, things like that, which means that one needs to go into the numerical data that we use and incorporate these effects as well from the simulation. So to really, really mimic the actual data that you will have. And in this context, we have a paper that goes in that direction of probabilistic neural networks, where you make a prediction of something, but it comes with an error bar, right? Because you add uncertainties of all those variables that come into your input. So your prediction is not just set on stone. No, there is this uncertainty. So I think that when you go into experimental implementations, the two keys are being able to model the limitations or the particularities of the experimental data in your training data set. That's first. And second, that with that probabilistic approach, you can get that range of uncertainty when you are actually using those models in the experiment. So yeah, it's ongoing work, but I think it's promising. But of course, that requires a lot of discussion also with experimentalists to really be able to incorporate all these things adequately. Yeah, thank you for the question.
Any more questions? Well, if not, then please join me in thanking Ricardo for an excellent talk, and great to have you with us. And all the best, and thanks everyone.
There was something in the chat. Okay.